We are doing this numerical question on gravitation. We have three mass points each of mass m. They are placed at the vertices of an equilateral triangle of side L. The question is, what is the gravitational field strength and the gravitational potential at the centroid of the triangle due to the three masses? Right? Okay, so we will have a diagram something like this. We'll have a triangle. I will draw an approximately equilateral triangle. Let us say this is the equilateral triangle, and there are 3 point masses at the vertices. This is mass 1, mass 2, and mass 3. And we'll call this mass A, B, and C. Right? The length of the triangle is L, so this will be represented by L. What is the gravitational field strength and gravitational potential at the centroid of the triangle? So I will now indicate the centroid of the triangle. Right, so I will try to get the centroid of the triangle. So this is the centroid, approximately the centroid of the triangle. We will denote this by O. Let us call this point D. Objective is to find out the gravitational field strength here and the gravitational potential. Okay? And the mass of each of these particles is m. Let us begin with the gravitational field strength. Right? Gravitational field strength we know is F by m. Right? The force acting on a mass per unit, force acting per unit mass. So I want to find out what will be the force acting on a mass over here. Right? Now the force that will act on any mass over here will be because of these three masses A, B, and C. So I will have to find out the net effect of these forces. Now we know that the gravitational gravitational field strength is force per unit mass, and I'll have to find out the force due to all these three things. So if I look at the force acting over here due to this, it will be in this direction. It's a vector quantity and acts along the center. We know these are central forces, so it will act along this particular line. This will act along this line, and this force will act along this line. And these are, let us call them FA, FB, and FC. Now, the three masses are equal, and the distance of these three masses from the centroid is also equal. Therefore, the magnitude of FA, FB, and FC is going to be equal. Right? So I can write down FA is equal to FB is equal to FC. I'm talking about the masses of the magnitude of these forces. Right? They will be equal because the force being applied is equal because these three masses have the same mass, and also the distance is same. So all these three forces are equal. Now, if I look at these three forces very closely, I can see an angle of 120 degree between these three. And by Lami's theorem, I can very easily say that the net force due to this F net will be equal to 0. That means if I add these three forces, Fa plus Fb plus Fc, I'll get 0. Right? Also, if you want to actually do that, what we can do is we can use law of triangle of forces. There are three forces, so we can law of polygon of forces. So I can draw these three forces, represent them in terms of vector, and graphically I can prove that. So if I draw Fa, let us say I draw a line of approximately 3 centimeters, right, whatever may be the magnitude. Then from this particular point, I draw the second vector. The angle is 120 degree. So somewhere it will go like this, right, of the same length, because the magnitude is 3. This angle will be 120 degree. Same I do over here, through an angle of 120 degree, I show force F. So this would be 90 degree, right, and 30 degree over here. What will happen is we'll see that this polygon closes, right, and therefore the net force F net is equal to 0, because if we add these three forces, we get 0. So what is observed is that the net force is 0, and therefore we can say that the gravitational field strength at the centroid is 0. Okay, let's move to gravitational potential. Now, gravitational potential we know is denoted by V and is given by Gm upon R. Right? Again, in this case also, the gravitational potential I have to find out because of all these three forces. We also know that gravitational potential is a scalar quantity. Because gravitational potential, another formula that we had was work done per unit mass. Now work or energy is a scalar quantity, mass is also a scalar quantity. Therefore, gravitational potential is a scalar quantity. It does not have a direction. So V is equal to W upon M, or V is equal to minus G upon M upon R. Now that would mean that to find out the net gravitational potential at this location, I will have to algebraically add all the three gravitational potential. Right? Here we had done a vector sum because gravitational field strength is a vector quantity. Here, since it is a scalar quantity, I'll do an algebraic sum for all the gravitational potential. Therefore, the V net will be equal to minus G. The mass is M, so I'll write M over here. But the distance from the centroid, from this point where we want to calculate gravitational potential, is AO. Right? To that, I will add the gravitational potential because of mass B, which will be again minus Gm upon BO minus Gm upon CO. So this will be the net gravitational potential at this location. Now I need to find out AO, BO and C. To find out these distances, we will use a little bit of trigonometry. What I'll do is I'll consider triangle ADB, which is a right angle triangle. Triangle ADB. This is 90 degrees. In this is equilateral triangle, so all angles are 60 degrees. So angle B will be 60 degrees. So if I take sine 60 will be opposite side, that is AD upon AB. We know that sine 60 is root 3 by 2 is equal to AD upon AB. AB is L. Therefore, AD is equal to root 3 by 2 into L. Now AD, right? Now AO is 2/3 of AD. This is the centroid, so AD is 2/3 of AD. Therefore, AO can be written as 2 upon 3 into AD. AD is root 3 by 2 L. 2 on. So this will give me AO as L by root 3. So I have obtained AO in terms of L by root 3. And we know that AO will be equal to BO equal to CO. Right? The distance from the centroid of all the three vertices is equal. So AO is equal to BO is equal to C. So if I go back over here, V net will be equal to minus Gm upon AO is L by root 3. So L by root 3 minus Gm L by root 3 minus Gm L by root 3. So this will give me 3 times, because all three are quantities, are 3 times root 3 Gm by L. So this will be the gravitational potential at this particular location, 3 into root 3 by Gm upon L, where G is of course the universal gravitation constant, M is the mass of each of these masses placed at the vertices, and L is the length of the sides of the triangle. This being an equilateral triangle, all the 3 lengths will be equal L. So we have found out that gravitational field strength at the centroid is 0, whereas the gravitational potential at the centroid is 3 root 3 Gm by L. Thank you.